We study one-to-one functions, and to understand what those are, we look at the definition. A function is one-to-one if no two elements of the domain have the same image. That is, whenever two domain elements are different, the range elements have to be different. So whenever x1 and x2, two x values, are not the same, then the two function values also cannot be the same. So here in this arrow diagram, you can see that the function g is not one-to-one because here are two different x values, 3 and 2, that have the same function value, 4. So we have g of 3 equals 4, and we also have g of 2 equals 4. And that just can't happen with a one-to-one function. What it means graphically is that if there are two different x values that have the same function value, so as in this picture, two different x values that have the same function value, so there's f of x1, that's the height, and there's f of x2, that's the heights are the same, which means that a horizontal line crosses the graph in more than one place. And there are lots of places on this graph where a horizontal line will cross in more than one place. So what we have is this nice horizontal line test, which is a direct result of the definition. If two x values are different, the function values have to be different. If they are the same, then that means that there's a horizontal line that crosses the graph in more than one place. And so the horizontal line test is a test for whether a function is one-to-one. So it's easy to tell from the graph whether a function is one-to-one, provided you can draw the graph. So just remember that a one-to-one function is a function that passes the horizontal line test. So what that means is that if you have two different x values, so here we have a graph, and we're going to look at two different x values. So here's one x value, and here's a different x value. So two different x values. But notice that those two different x values have the same function value. And we see that because we see that there's a horizontal line that passes through the graph at that height, touches the graph in two places. And so this function is not one-to-one, not one-to-one, because there are many horizontal lines that cross this graph in more than one point. And so that means the function is not one-to-one. The function is only one-to-one if whenever you have two different x values, you have to have two different function values. And so that's what one-to-one means. And so if you can take this part away, horizontal line test for a one-to-one function, we want to know whether a function is one-to-one because only one-to-one functions have inverses. And we want to study the inverses of functions so that we know how to undo the effect of a function, because that's what an inverse does. So here we have f inverse of y equals x means that f of x equals y. So for f inverse of y equals x, we have the ordered pair yx. But for f of x, we have the ordered pair x, y. So that tells you that if there's an ordered pair in one of these functions, then reverse the coordinates to get an ordered pair in the other function. So if you know that yx is an ordered pair in a function, then you know that xy is an ordered pair in the inverse of that function. F and f inverse are inverses of each other. So you think about the function f taking this domain A to this range B. Then the function f inverse takes the range of f, which is B, and treats it like its domain, and carries that over into the domain of f, which is A, which is the range of f inverse. So we have these two statements. Now, since the ordered pairs are just reversed, we see that if we have f of 2 is equal to 7, that means we know that in f we have the ordered pair 2, 7. So that means in f inverse we have the ordered pair 7, 2. So f inverse of 7 is 2. Here we know that f inverse of 3 is negative 1. So in f inverse we have the ordered pair 3, negative 1. And so in f we must have the reversed ordered pair negative 1, 3. And so f of negative 1 is 3. Okay, so when you draw the graph of an inverse function, you make use of the fact that the ordered pairs are just reversed. So here in this graph, we are asked for f inverse of 2. So we have to remember that this 2 is actually on the y-axis. because if we have f inverse of 2, it means that that 2 is on the y-axis of the function f. So you're looking at 2 on the y-axis, and you're finding the point on the graph that corresponds to 2 on the y-axis, and that's the point here, and the x-coordinate of that point is 6. So f inverse of 2 is 6. F inverse of 2 is 6. So f inverse has the ordered pair 2, 6. Now f inverse of 5 means you find 5 on the x-axis, and 5 is right here. And the point corresponding to 5 on the graph is this point, and the x-coordinate of that point is 2. So f inverse of 5 is 2, so f inverse has the ordered pair 5, 2. Whereas f has the ordered pair 2, 5. And then finally f inverse of 6, find 6, and that's on the y-axis. So that's going to give you the y-coordinate 6 and the x-coordinate 0. And so f inverse has the point 6, 0. Now if we plot these points, and first let me erase the, I guess I can't use the eraser on that, I have to use the, okay, so if we, oh, I didn't want to do that. Well, we'll just leave it there. So if we plot these points, 2, 6. Okay, so we plot 2, 6, and that gives us, let's see if I can make it, if I can put it exactly where it belongs. 2, 6, right there. And then 5, 2 is going to be right, try to do a good job here, 5, 2. Pretty good. And then 6, 0 is going to be 6, 0, about here. Okay, so now we have to figure out how to connect these dots. So this point here, this point which is 6, 0 corresponds to the 0, 6, and the point here corresponds to the point 2, 5, that's 5, 2, so we just connect those two dots just with that segment there, connect these two dots with that segment there, and that's the graph of the inverse function. Okay, so to show that two functions are inverses of each other by using the inverse function property, you do the composition. So you do f of g of x. And f of g of x is, of course, you're going to put g of x where you see the variable. So here I see the variable 2x. I'm going to put 2 times g of x, which is x plus 5 over 2 minus 5. All right, so here we have 2 over 2, so that gives us x plus 5 minus 5. And of course, x plus 5 minus 5 is x plus 0, and x plus 0 equals x. So we've shown the first part of the inverse function property. We've shown that f of g of x is equal to x. So now we have to look at g of f of x. And so that is, go and put f of x into g. So here I see the variable, so I'm going to go, I have to write 2x minus 5 plus 5 over 2. Of course, 5 minus 5 plus 5 is 0, so you get 2x over 2, which 2x divided by 2 is just x. And so again, you have g of f of x equals x, and that's exactly what you have to show by the inverse function property. That's exactly what you have to show in order to conclude that your two functions are inverses of each other. Now, when you're finding the inverse function, you make use of the fact that if f has the ordered pair xy, then f inverse has the ordered pair yx. So that means all the y's become x's. So here, f of x is y equals 2x plus 1. You can rewrite that by just changing the y's to x's. So x equals, and then change the x's to y, 2y plus 1. And now just solve for y. So you'll get x minus 1 over 2 equals y. So that means that this function that I just wrote, this x minus 1 over 2, is the inverse of this function, y equals 2x plus 1. For this next one, I think I told you before, at least I hope I did, that there's a typo here. We should have that x is greater than or equal to 0, because otherwise we don't have a one-to-one function. So the graph of 4 minus x squared with x greater than or equal to 0 will be the graph of a one-to-one function. And so that means we can find the inverse. So we set y equal to 4 minus x squared. And now we are going to interchange x and y. So x equals 4 minus y squared. So x minus 4. I don't really want to do it that way. I want to have a positive coefficient for the y squared term. So I'm going to move the y squared term over there. Y squared equals, and I'm going to move the x term to the other side, 4 minus x. Now, as long as x is less than or equal to 4, I will get a positive value here for 4 minus x. X has to be greater than or equal to 4 in order for me to be able to say that y is equal to the square root of 4 minus x. And I'm going to use the positive square root because my y has to be greater than or equal to 0 as well, since my x is greater than or equal to 0 over here. So I'm going to use the positive square root of 4 minus x, and I'm going to have, of course, x has to be greater than or equal to 4, or I'm sorry, not greater than or equal to 4, I said less than or equal to 4. X has to be less than or equal to 4 in order for the 4 minus x to be positive. So x has to be between 0 and 4. At any rate, this is the inverse function of, the square root of 4 minus x. And then finally, x over x plus 4. To find the inverse function for that, I need a little more space here, so I'm just going to zoom in on this. Okay, so we set first y equals x over x plus 4. Now we interchange x and y, so x equals y over y plus 4. Now multiply times y plus 4 to clear the fractions. X times y plus 4 equals y. Use the distributive property, xy plus 4x equals y. Group the terms that have y on the same side, so I'm going to put the xy term over there. So I'm going to end up with 4x equals y minus xy. Now factor out the y. 4x equals y times 1 minus x. That's factoring out the y here on the right-hand side. And now divide by 1 minus x. So 4x divided by 1 minus x equals y, and there's your inverse function. You can actually show by the composition that these two functions are inverses of each other. I'll leave that to you as an exercise. And so now, to sketch the graph of f, and then use that graph to sketch f inverse graph. Remember that if two functions are inverses, they have the property that the x and y coordinates are switched, or reversed. So the square root of x plus 1, remember, is a shift to the left 1 unit of the square root of x. So it's going to go through -1 on the x-axis right here, and it will equal 0. Well, when x equals 0, you're at 1, so 0, 1 is there for the y-intercept. So here's the x-intercept and also the beginning x value, -1. X can't be less than -1. And here's the y-intercept. And the graph is that curvy, sort of half of a parabola, actually, is what it is. The other half is the negative square root, which is that one right there. But we're looking at the positive square root of x plus 1, so I'm just going to erase this. So, so there's the graph that we're interested in. Now for the inverse function, we just have to remember that the inverse function has the reversed ordered pairs. So for instance, this ordered pair, -1, on the graph of f, will become the ordered pair 0, -1, on the graph of f inverse. So f inverse goes through that point right there. And that point corresponds to this point, -1, 0. So you do that and you find it. The point that corresponds to the y-intercept, which is 0, 1, will be the point 1, 0. So 1, 0 here is the x-intercept, and that corresponds to this y-intercept. So notice if I draw that line there, that little dashed line. So what happens is that whatever the amount of bend is right here is reflected through the origin, it's reflected through the origin, and becomes the kind of reverse bend over there. And so what happens is you can see the graph of the inverse function is going to be like that, because every point that is here on this graph has a reflected point on the inverse function graph. So you see those points and how they reflect each other, and they're reflecting across the origin like that. And so we have we have symmetry through the line y equals x. So you can reflect the graph of the red, which is the square root of x plus 1, and you can reflect that through this line of symmetry and get the blue graph, and that's the graph of the inverse function.